Hi, I'm Avgustin Raiо. I'm an associate professor of philosophy at MIT. And today I want to talk about how there are some infinities that are bigger than others. So, a first exercise to see why some infinities are bigger than others is to think about Hilbert's hotel. So Hilbert's hotel is like an ordinary hotel, except that instead of having finitely many rooms, like most hotels, it has infinitely many rooms. So we can draw this just having a very long rectangle with lots of rooms, and we're gonna number each room with a natural number. So the first natural number is 0, after that comes 1, and 2, and 3, and 4, and 5, and so forth. And I'm going to assume that this hotel is completely full. So in other words, every room has a person inside it. So I'm going to draw a person inside each room. And I'm going to assume that these various persons are numbered 2. So maybe each of them is holding a piece of paper with a number. The person in room 0 has a piece of paper with 0 on it. The person in room 1 has a piece of paper with the number 1 in it, and so forth. So now ask yourself this question. What would happen if an extra person were to come to the hotel? Could they be accommodated? Now, in a finite hotel, the answer is no, because all the rooms are already occupied, and we can assume that these are prickly guests and don't want to share rooms. But in an infinite hotel, it can be done. So think of it this way. We can just ask each person to move one room to the right. So Mr. 0, who's now in room 0, moves to room 1, and Ms. 1, who's now in room 1, moves to room 2, and 2 moves to 3, and 3 moves to 4, and 4 moves to 5, and so forth. So then the result is that all of our original guests are in rooms, but our first room is vacant because now there's nobody in room 0. So we can welcome our additional guest. One thing that's amazing and worth emphasizing is that the hotel was full at the beginning, and we could still fit in more people. That's amazing, but true. Part of the reason that's possible is that there are two things that come together in the finite case, but need to be kept apart in the infinite case. So in the finite case, if you have a set and you add some extra things to the set you get is bigger than the original one. But in the infinite case, that's not necessarily true, because have your original set just consist of the original hotel guests, and then add one more. The new set isn't bigger in the sense that you can still put each element of the new set into a different room in your hotel. So if you measure size in terms of how big a hotel you would need to accommodate the members of the set, then we need to conclude that the set of the original guests and the set of the original guests plus 1 are of the same size. Crazy. It's this amazing thing. And if you think of it, you can see that we could have accommodated any finite number of new guests too, because suppose we get 700 new guests, then we can just ask each of our original guests to move 700 rooms to the right. But wait, what if we got infinitely many new guests? Okay, so suppose that we have infinitely many new guests, and they too are numbered with the natural numbers. So the first one is holding a 0, and the second one is holding a 1, and the next one is holding a 2, and so forth. How could we accommodate them? Well, we can do it like this. We just ask each of our original guests to move to the result of multiplying their current room by 2. So the guy in 0 goes to 2 times 0 equals 0, so he stays. The person in 1 moves to 1 times 2, that's 2. So she moves 1 to the right. And the person in 2 moves to 2 times 2, that's 4. She moves 2 to the right, and so forth. So the result of this is that all the old guests are occupying even-numbered rooms, and all the odd-numbered rooms are free. So we can ask each of the new guests to go to an odd-numbered room. Which one? Well, they can just look at their number, multiply it by 2, and add 1, and they can go to that room. So here's the lesson of this. The lesson of this is that if we have an infinite hotel, we can accommodate 1 copy of the natural numbers, but we can also accommodate 2 copies of the natural numbers. And in fact, we can accommodate as many copies as the natural numbers as there are natural numbers. But before tackling that question, it's useful to consider a different one. And this is the first of 2 wonderful theorems that were proved by Georg Kantor in the 19th century. The first theorem is that you can put the rational numbers in 1-1 correspondence with the natural numbers. Now, what is a rational number? A rational number is a number of the form a over b, where a and b are both natural numbers, and we assume that b is not 0. So what Kantor did is show that we can pair up the natural numbers with rational numbers with no remainder. Every natural number gets a unique rational number, and every rational number gets a unique natural number, and nobody's left out. So here's how to do it. We simply draw a matrix, and each column is going to correspond to a numerator, and each row is going to correspond to a denominator. So this is how you fill out the matrix. And so forth. So you can see that every rational number is on this matrix. Because remember, you get a rational number by taking a natural number and dividing it by a natural number different from 0. Suppose your rational number is 17 divided by 94. In order to find the cell that corresponds to that number, just go to the column that's labeled 17 and to the row that's labeled 94. And that's where your number is going to be. So every rational number is on the matrix. So what Kantor discovered is that you can assign a natural number to each cell. And here's how to do it. Just diagonalize. So have this one be 0, and this one 1, and 2, and 3, and 4, and 5, and 6, and 7, and 8, and so forth. Using this system, every rational number got assigned a natural number. So now we can come back to our hotel. So remember, our question was, how could you fit infinitely many infinities into your hotel? Well, now we have a way of doing it. So think of each column on our matrix as corresponding to 1 infinity of new guests. In order to decide which room to send a person to, all you need to do is use Kantor's trick. So assign a natural number to each cell in the matrix and ask the person to go to the room corresponding to that number. So there, we fit infinitely new infinities of guests into our hotel. Amazing!